Yeah.
Good afternoon to all. It is a pleasure to introduce Dr. Shiv Sarkar to deliver the concluding talk of the conference. Dr. Shijan is assistant professor in the Department of Mathematics, IIT Palakkad. He obtained his PhD from ICOST Bangalore under the guidance of Professor Joydeep Sarkar. Before joining IIT Palakkad as an assistant professor, he was an inspired faculty at IIT Bangalore. So over to Dr. Shijan.
Okay, thank you, Geetika. Okay, so this is the first time I'm being the last speaker of the conference. So I don't know what else to say other than congratulating the organizers for doing such a fine job. And also I'm thankful to Dr. Narayana, one of the organizers who invited me to give this talk. Okay, so as the title suggests, we'll be focusing on two problems related to the Hardy space over unique polydisk. So this is a joint work with my academic brother Ramlal Devnath, who is now at 88 Stockholm. So obviously the setup of our discussion is this Hardy space. So I'm sure like many of you have seen this Hardy space. So I won't keep spend much time into describing it, but it can be alternatively realized as the collection of all analytic functions on the open unit disk such that the coefficient satisfies this kind of growth condition. And we also denote by H infinity D as the collection of all bounded analytic functions on the unit disk. And this is one of the most natural and also on the other hand one of the most important operators on the Hardy space over unit disk. It is just the multiplication by the z coordinate, or in other words known as the shift operator. So before going straight away into the results that I want to discuss, I would like to spend some time on why we should study Hardy spaces. Like there may be some of the participants who are looking at Hardy spaces for the first time, so it is meant for them that why it should serve as an interesting space. So suppose you want to extend your life by not looking at only finite matrices but also infinite matrices. So suppose you have an infinite matrices and you want to understand when it acts like a bounded operator on little L2. So this kind of study was initiated by Otto Tokles, and he was looking at infinite matrices which is symmetric and whose entry satisfies this kind of a relation, and showed that this kind of an infinite matrix will be a bounded operator if and only if there exists a L infinity symbol whose Fourier coefficients are exactly these entries of the matrix. And just this correspondence led to a lot of development, and later Brown and Halmos extended this for any arbitrary matrices, infinite matrices whose entry satisfies this kind of a relation. And this is what known as the Tokles matrix. And what is very beautiful about this thing is that you can make sense of this infinite matrix as a very well-defined, nice bounded operator. And you can ask questions for this infinite matrix and look at the corresponding bounded operator and pose questions there. So there is a very nice correspondence which was much more strengthened by in the same paper by Brown and Halmos, saying that these kind of infinite matrices correspond to this kind of Tokles operators, and this kind of Tokles operators determine this kind of an algebraic identity. So this algebraic identity essentially says that since this is an infinite matrix, if you remove the first row and the first column, it should be exactly the same copy of the matrix, which is evident from the picture here. And now you can ask many questions about this infinite matrix, like when this infinite matrix may be upper triangular. So this you can characterize by saying that this is upper triangular if there is Tokles operator, the adjoint of the Tokles operator commutes with the shift operator. So in that way you can ask many questions for infinite matrices by going through Tokles operators. Another thing that Hardy spaces is very much useful is identifying or understanding abstract operators on Hilbert spaces. So like many of the speakers before have said that isometries can be broken down into two pieces like a unilateral shift and a unitary operator. And this is actually a consequence of the whole von Neumann decomposition, that any isometry up to unitary equivalent is just the direction of a shift operator on some kind of a Hardy space plus unitary on some space. So like you have an abstract distance preserving linear map on a Hilbert space, and you can essentially write it in terms of this very simple operator. So, and there is another something called an Evelina-Fick interpolation. So suppose you have a n collection of pair of points coming from the unit disk, and you want to interpolate the data by saying that I want a bounded analytic function which takes zix to wi, and this is the main requirement. Like this is the main optimization problem, that you are trying to get hold of a bounded analytic function whose norm is less than equal to 1, which takes zix to wi's. And the solution of this kind of an interpolation problem exists if you can say that this kind of a matrix behaves in the positive semi-definite manner. And there was a solution given by Donald Saracen, who proved this interpolation theorem by some kind of operator theoretic argument called the Commutant-Dilting theorem, and it is essentially studied on Hardy spaces. So it is very much evident that if you are interested in function theory or over the unit disk or over some other domains, one of the approach can be identifying some kind of a Hardy space and trying to go through some operator theoretic argument. Oh, sorry, there's a typo. This is WIWJ bar. Okay. And another thing that was mentioned by Professor Jaidev Sarkar in his talk, the kind of von Neumann inequality that we have for distinguished varieties. So basically, Angler-McCarthy in their very remarkable paper showed that this kind of domains, this kind of curves, suppose this is the Leeds parabola, this can be described in this manner. That is, so there exists a matrix-valued rational inner function such that this Leeds parabola can be understood as the determinant of this polynomial. So, and there also Angler-McCarthy used the Nash-Walsh model theory, which is also another operator theoretic technique based on Hardy spaces. So with all this serving as a motivation, I will now jump to the discussions once more, the things that we are interested for this talk. So basically, so these are the Hardy spaces and shift operator, and you also have inner function that the modulus is 1 almost everywhere on the unit circle. And so an example can be the finite Blaschke product. So you may have come across this when you are looking at disk automorphisms. So this kind of functions are typical examples of inner functions. And this was one of the stepping stones for a generation of results to come. It is called the Berling's theorem, like who Berling proved that any MZ invariant closed subspace of H to D. So MZ invariant means MZ will take S to S. So any S is MZ invariant, okay. MZ is contained again in S. So any invariant closed subspace is of the form theta H to D, where theta is the inner function. And so this equivalently says that any MZ star invariant closed subspace of the Hardy space should also look as the orthogonal complement of subspaces of this form theta H to D. And it was Helmholtz's ingeniousness that he found that this Berling's theorem is actually consequence of the whole von Neumann decomposition of isometries. So Berling's theorem, the original proof is very much function theoretic, but Helmholtz gave an operator theoretic viewpoint and found the result, that is a generalization of the Hardy space over unit disk to the vector valued setting as well. So now the question is higher dimensions, right? So we move to the disk, to the polydisk. You can always make sense of a Hardy space in an analogous manner. And the essential fact that is very much useful, that you can write this Hardy space over unit polydisk as tensor products of Hardy spaces. And if you have any invariant subspace in this setting means that it is invariant under each of these coordinate multiplications. Okay. So now the natural question is, does Bernoulli's theorem hold when we are going for domains outside the unit disk? And the answer is no. This is a very simple example, counter example by Rudin. If you just take this function and you just generate the subspace building on this function, then this subspace cannot be written as theta times h to d2, where theta is a Dirac function. And Rudin gave many lot of counter examples which are very exotic nature, so playing with functions that serve as a counter example. So now, given any invariant subspace, we have the natural collection of operators which are called the restriction operators. And following Helmholtz's step, so whenever you see Sarkar in this slides, it is Jaidev Sarkar, not me. So his reference. Yeah. So basically, they could find a condition which characterized all the Bernoulli type invariant subspaces of the Hardy space over unit polydisk. Like this was done by Mandrekar for n equal to 2 case for the bidisk case, and Sarkar, Vik and Sasane did it for general n cases. So basically, this Bernoulli type of thing, if you are expecting, you need to find some kind of operator theoretic phenomena to happen. Otherwise, this is not always true in general. But this is also the first of many results that says that, okay, so now we know that the invariant collection of invariant subspaces on the Hardy space over unit polydisk is very complicated. But there is one result like this that saying that if you put enough operator theoretic conditions on these restrictions, then you can tell something. So this opened the avenue by asking that whether we can classify invariant subspaces of the Hardy space over unit polydisk by somehow identifying operator theoretic conditions on the restriction operators or some other operators. So now suppose you have this theorem. So basically you have this inner function as well. So the natural question that one can ask is that when does this theta, which is an inner function, depends on a particular variable, right? So Bernoulli's theorem or this Mandrekar-Sarkar's theorem, they're saying that there will exist some theta, but we don't know what properties. This is kind of an existential theta. But what happens in most of the arguments related to operator theory that you may have come across certain subspaces and somehow you have proved some nature of it, like the Bernoulli's theorem and everything, but you want to extract more and more information about that function. So like one of the information can be whether this inner function is depending on a particular variable. So this was not known, or people did not study in this particular direction, and this was the first question that we started this work with. So for this we needed to introduce some more operators, like the restriction operators were not enough to give you that extraction of that property. So this is nothing but the evaluation function. So you are evaluating a function of the Hardy space at the 0th point, where 0 is coming at the jth coordinate. So this is nothing. You take any function, you evaluate it at 0 based on the coordinate, and that is just the image. There's a typo. This is the evaluation operator is defined from the Hardy space to the invariant subspace S. And this evaluation math can be written as this identity minus mzj star, which is nothing but the defect of the shift operator by the jth coordinate. And using this evaluation, you can create an operator which is just you are evaluating function at 0 in the jth coordinate and then pulling back the function to your subspace, right? So basically, how is the approach going? So you have an inner function theta, and you consider this S to be theta h to dn. Now this is the invariant subspace. Now you create this evaluation operations. And you have this collection of defect operators associated to the restrictions. Then if you take the product of the evaluation operator and the defect of the restriction operator, then you see that the product is coming out to be a certain nice manner, like projection, MZJ. So basically it's a self-adjoint operator, and the product is coming out to be a nice manner. And this is what we noticed first, that invariant subspace will be of the form theta zi times the Hardy space if and only if this product vanishes for all coordinates except function is dependent. So this is very much surprising. Coordinate, but your conditions are coming on all the coordinates except for that coordinate. So, I'll try to give a sketch of the proof because it's not that hard. So basically, if you start with the converse direction, so whenever your invariant subspace is of this form, that theta zi times the Hardy space, then it will obviously be MZJ reducing for all j, all the coordinates outside the set I. So what is reducing? Reducing means that it is invariant as well as it is invariant under the adjoint. So basically, if a subspace is MZI reducing, then one of the equivalent way of understanding is that it will commute with the shift operator. So the projection will commute with the shift operator depending on the particular coordinate. So therefore, we can immediately see, so then since this projection and these projections are orthogonal, right? So whenever we have the commutativity of these projections, this projection will come here, and because they are orthogonal, they should nullify, they should vanish. So for subspaces like this, so this is obviously a necessary condition. And why this is sufficient, we can look at it that if this product is equal to 0, then because this is operator of this form, you can treat it as A times A star. So this will imply that the A is equal to 0. In other words, this PS and ZJ PQ is 0, which is equivalent to saying that the projection onto S will commute with the shift operator on the jth coordinate. So this will imply that this subspace is MZJ reducing for any j except for I. And that, using that, you can show that this restriction operators will always doubly commute, like this RZK will commute with this RZJ star. In other words, this subspace, on-breaker, circle, and all those properties. So if we have subspace, so there should exist some theta in our function, such that the subspace should look like this. So now we have to somewhat ensure that theta should depend on a particular ith variable. So now this step to that S is MZJ reducing, and using the fact that S is of the form theta is to n, this will go using these two things. You can say that this MZJ should commute with the adjoint of the multiplication operator, and this essentially will give you this kind of identity. When you take this function to be the Zego kernel for the Hardy space over polydisk, then it essentially gives you this kind of a identity, that theta w bar is equal to theta wj hat bar, where wj hat is nothing but you have 0 in the jth variable. So now j was any arbitrary coordinate which is not I. So this should happen for every j except for the ith thing. So that implies that theta w should not depend on any other variable outside I, right? Because this is happening for any wj, where j is not equal to I. So therefore, since w was arbitrary, theta z was not dependent on the variable zj, and j was also arbitrary outside I. So your subspace, invariant subspace, should be of the form theta zi h to dn. So that is, your inner function should be only depend on the ith variable. So basically what this essentially is saying, that you need not consider about invariant subspace, you need not consider about anything. You just take a inner function theta, which is a function theoretic element. You just want to ask that whether that function depends on a particular variable, and you can find the answer through this approach via the Hardy space over unit polydisk by finding a operator theoretic equation that facilitates that. So now, so another class of invariant subspace that you can build in the polydisk, bidisk or tridisk setup is that you can combine this one variable Berlin type invariant subspaces and take combinations of those. So suppose you have a collection of one variable non-constant inner functions and you consider this subspace, that is the summation of all these individually Berlin type invariant subspaces, right? So obviously one can show that this kind of invariant subspaces where phi i's and phi n's are not constant, they does not satisfy the doubly commutativity property that is essential for Berling's theorem on the polydisk. So therefore this class of invariant subspaces are such examples which are beyond Berling spaces. And corresponding to that, I have already shown what are quotient, so closed subspaces which are invariant under the adjoint. And when you have a quotient space, then you can, instead of the restriction, you can focus on compression of operators. And this identification of this subspace was somehow related to this property of quotient subspaces. It's essentially asking that when does a quotient space, quotient invariant space, factorize into the tensor product of n copies of quotient spaces. So remember that when I was introducing Hardy space over unit polydisk, it has an identification as tensor product of Hardy spaces. So essentially you want that whether that same kind of identification can be pulled back to the quotient spaces. And this characterization for n equal to 2 was done by Izuchi et al. And Sarkar in 2014 for general cases, that any quotient invariant subspace can be factorized into tensor products if and only if we have another doubly commuting kind of a condition, but instead of the restriction, we are focusing on the compression operators. So as long as you have this compression kind of doubly commutativity of the compression operators, then your quotient space will factorize into a tensor product. And now since each QI's are sitting inside the Hardy space over unit disk, and we have Berling's theorem there, so therefore each QI will be actually the orthogonal complement of phi I times H2D, where phi I is an inner function, using the Berling's theorem. And using that, one can essentially show that any invariant subspace is of this form, of this summation form, if and only if this doubly commutativity happens, where Q is the quotient space. So basically, you are trying to characterize subspaces, but you are getting a characterization based on the quotient spaces. So therefore, an immediate and natural question is that whether you can characterize these subspaces intrinsically, like if you can determine some conditions on the restrictions, and if at all other operators, that should be only dependent on the subspace, not on the quotient space. So, and here we can also fix so as you can see that in this results, we don't have a choice of which coordinates are appearing. It's totally fixed for this I equal to 1 to n, where n is the dimension of the domain. So but here we can extend the identification result by choosing coordinates where these functions are dependent on. So suppose your invariant subspace are now summation of this Berlin type invariant subspaces where these functions are dependent on your favorite choice of coordinates, right? And then we could characterize saying that an invariant subspace, an invariant subspace should be of this form if and only if it is satisfying the same kind of condition that we saw earlier for all the coordinates outside this lambda set. And for this lambda set, this EI times RI, they should satisfy this kind of a condition, that the product of this EI RI times EJ RJ, this should be 0. Now the main important fact is that all these operators are dependent on the subspace S and not the quotient spaces. And in a certain sense, these conditions says that the product of the defect operators commute. So basically, you are having some kind of a doubly commutativity kind of condition, but depending on you need to introduce some kind of evaluation operators to get the result. So as a corollary, if you want your subspace to look like this, summation of phi I z I h to dn, where I is varying from 1 to n, then you need not look at this condition anymore. This is only necessary and sufficient to characterize subspaces of this form. So you can determine the dependency of the coordinates of these inner functions via this kind of operator theoretic condition. So that's the main thing. So now this kind of commutativity of certain kind of defect operators. Okay, one more thing that I want to say, like this kind of subspaces, they are also in a certain way special because they satisfy this kind of identity and not this. Because this will always imply that it's a Berlin type invariant subspace. But since this is a subspace not of the Berlin type, so this is not zero. But surprisingly, if you take square of this operator, then this will always be zero for this kind of invariant subspaces. So now it goes, so in my title there was two problems, so one problem is over, so we will focus on the next problem. So next problem is commuting projections, and how much time is left? 10 minutes, okay, good. So basically, so for an invariant subspace, you have the restriction operators, which are isometries. So therefore this RZI, RZI star, these are projections, right? So when you have two projections in your hand, one of the most natural questions that you ask where those two projections commute with each other, right? So basically, you have an invariant subspace, you have the corresponding restriction and the corresponding projection operators. So when do they commute? So in general, this is a hard problem. But also, one can easily see that if you have a Berlin type invariant subspace, then this RZI star and RZJ should commute with each other. And for Berlin type invariant subspace, this thing holds. But what about in general spaces? So as I said, in general spaces, this is still not known. This is an open problem. But if we are considering subspaces of this manner, then we do have a nice characterization that if you are considering this particular type of subspaces, which are combinations of one variable Berlin type invariant subspaces, then for this kind of subspaces, the projection should commute if and only if these functions phi I and phi j should vanish at the 0 points. Right? So see, this I and j is not now varying over the set of all coordinates. You are just choosing one of i's, you are choosing another j. Those I and j just need to be distinct. So basically, you are not looking at tuple of all operators. You are just taking any two projections. And any two projections will commute if and only you have this just simple criteria that it should vanish at 0. So now, although this thing is very much simple to see, but the proof is quite long, and unfortunately neither do I have the space or time to give you the sketch, but it requires a lot of orthogonal decompositions and playing with that inside this space to come out for this kind of a result. So essentially, so now if you have this kind of invariant subspace, then you can always ask that whether the tuple of orthogonal projections corresponding to your favorite chosen set of coordinates, when do they commute with each other? And because of this thing holds, you can say that it should vanish at 0 for all of these functions. And similarly, if you are looking at the subspace where you don't want any dependency on the coordinates, then the only criteria is that this phi I should vanish at 0 for all 0. So essentially, this is another example of this very interesting direction, is that you take out functions, you want to say something about functions, but you go via approach operator theory. So essentially what this is saying, that if you have a collection of one variable inner functions, and you want to understand when they vanish at 0. In other words, when do they have a Zi factor coming out of them. And this is something that you can say, like you can associate a Hardy space, you can associate an invariant space, identify certain class of projections, and say that this kind of a factorization happens if and only if these projections commute. So this commuting projections thing also recently came up in some other aspects of this correspondence between function theory and operator theory. So Ronald Douglas, he asked these questions that if there are suppose two inner functions of the unit polydisk, and you have the corresponding orthogonal projections onto their quotient spaces. So this is one kind of a Bernoulli type invariant subspace, this is one type of a Bernoulli type invariant subspace, and you are taking the orthogonal projections, and you are just asking when the product of these two projections becomes a finite rank projection. And the straightaway approach is that before solving this question, you first ask when do these individual projections commute? Because for the product of projections to be a projection, one of the things that we want is that this projection should commute with each other. And this was recently solved by Jaideep Sarkar, Ramnath Devnath and Deepak Pradhan. So if you take only the unit disk, then this happens when either phi divides psi or psi divides phi. So these orthogonal projections will commute in one of the cases where phi is a factor of psi or psi is a factor of phi. So these are the two possibilities. And if you are going beyond the one dimension, then this kind of happens for a little bit of non-trivial way. So basically this kind of projections commute if and only if there exists a trigger of inner functions where this phi tilde and psi tilde are dependent on disjoint variables, and you have this kind of a factorization that your initial inner function can be written as phi tilde times theta, and psi can be written as psi tilde times theta. So theta is a common factor for both of them, but phi tilde and psi tilde are different, and not only they are different, they are depending on disjoint set of variables. So that is a certain kind of a special kind of a factorization that you are having. And using that, they could show that they could answer the question of Douglas that this, if we are looking at if n is strictly greater than 2, then this product is never finite rank for any non-trivial way. And if n equal to 2, then this product becomes finite rank either when phi 1 and phi 2 are constants or they are finite Blaschke products dependent on disjoint set of variables. So finite rank of the projections and commutativity is essentially pulled down to the fact that your inner function is very nice, that it should be a finite Blaschke product, and the commutativity is coming in the feature of that they are dependent on disjoint set of variables. So now this again spurs the general question that if you have two invariant subspaces, obviously you can associate two orthogonal projections corresponding to them. When do they commute with each other? So this is the general question. So we tried solving it for this class of invariant subspaces, this summation of one variable Bernoulli spaces, and we could first identify that for these kind of invariant subspaces, the orthogonal projection should commute with each other if and only we have the one variable phenomena that phi I divides psi I or psi I divides phi I. And now we can pull this result, which is dependent on all the coordinates, to subspaces which are dependent on your favorite set of coordinates, and you can just say that this will commute if and only if this kind of a thing happens, not for all indices, but the indices which are coming from the intersection. And using this, we can characterize the finite rank question, that if your subspaces are looking like this combination of one variable inner functions and Q1, Q2 are the corresponding quotient spaces, then this product will be a finite rank projection if and only for all the coordinates coming outside the intersection, they should be finite Blaschke products, and any coordinate that is coming from the intersection should either phi j should divide psi j, and phi j should be a finite Blaschke product, or psi j divides phi j and psi j should be a finite Blaschke product. So these are essentially the questions that we solved in our in this topic, and this kind of discussion gives us these open questions that are open in general, and if anybody is interested, they are encouraged to try. So our method does not work to say that any inner function is dependent on a particular pair of variables. Like our method, our strategy was asserting only when your inner function is dependent on a particular variable. But suppose you want to say whether your inner function is dependent on the second variable and the third variable, then our strategy won't work. So you have to find a new kind of operators or new kind of operator theoretic conditions which can guarantee that your inner function depends on the particular set of variables. So this is still not figured out. The next question is obviously you want to understand the characterization of invariant subspaces for which the square of these commutators vanish. So as we see the summation of one variable Burning type subspaces, for those kind of subspaces this is obvious, this is true, but are these the odd kind of subspaces? So this is also a very lingering kind of a question that whether the square 0 will obviously imply that whether the subspace should be of this form. And obviously this is a very hard question, but one of the most interesting questions that one can come across just after the Burning type of theorem, that can be characterized invariant subspaces for which the projections corresponding to the restriction operators commute with each other. So these are the references. So this is Burning's original paper. This is the Manfricker's paper for n equal to 2, where he proved Burning's theorem for Hardy space over by this. This is the paper where they proved this factorization of the quotient spaces into tensor products. This was the extension for any general n, also in a similar direction. And this is the paper where the commutativity question was solved. And this is our work with Ramlal. And also I would like to highlight that anybody interested in Hardy space over unit by this for multivariable things, you can go to this very nice survey article edited by Ronge Young. There are many questions that are still open, that are difficult, but you can get a very good perspective of what is there and what is not there. Okay, I'll end my talk with this. Thank you.
Are there any questions for the speaker?
So the product of the projections means the range of the intersection. So will be, again, you can write it as a summation of this invariant subspaces depending on the section. Yes.
Is there any other question? If not, then we have come to the end of the last invited talk of the conference. Let's all thank the speaker.
Thank you. I invite the chair to present a token of appreciation to the speaker. Now we are moving on to the contributory sessions. There are two venues. Venue 1 will be here and venue 2 will be the first floor. Participants, please be on the respective venue by